At 6 o'clock, let's get going. Thanks again for coming. 6 o'clock at night's tough, so thank you. I appreciate it. Yeah, so second last lecture with me. I finish up next week, so hopefully we're gonna have to kind of race through section 3. So if there's anything, I guess it's kind of hard to tell, but if you've looked forward in the notes, if there's anything you want particular extra help with, particularly if it relates to anything to do with the homework coming up, let me know and I can try and jump around a bit to make it a bit more targeted. Otherwise, I'll just waffle on. Yeah, today I'm hoping to get through up to floating point. We'll just talk a bit about basic scientific computing environment. I'm not going to talk too much about that because you'll all be really familiar with it. Basically knowing, whatever magic spells, from making nice plots in Matplotlib, how do you do that in Julia? That's pretty much all you're going to need to know, how you make some plots. Data frames and some basic data formats. So we're going to go through that bit really quickly and I'm going to try and get up to floating point. And then next week, we're going to do a little bit about integration, differentiation, and linear algebra really quickly. So has anyone done any of numerical stuff before? Is that new? Hopefully not in any other courses. Do you do that stuff? Anyone not done it before? Not touched it before? They're looking at question 15 and 16 and feeling traumatized. Has anyone done 15 and 16 yet? No. Okay. Well, I'll talk a little bit more about those because they were my special questions. I had an announcement from Yoni that he was going to record the practicals for anyone who can't make it to them coming up. So they're going to end up on YouTube. So I don't 100% know the context of what's going to be in it, but it's useful for the homework, I assume. Okay, cool. Any questions or just charge on? Yep. Oh, that must be it. So he's recording it. So it's going to end up on YouTube. So I missed that. I had my public holiday yesterday because I live in Moreton Bay. So go figure. Anyway, yeah, cool. So that's how it's going to work. Okay, good. You're on the ball. I'm not quite done yet. Anyway, great. Okay, awesome. All right. So section 3. Oh, not that way. I want to go forward. No, I'm moving around. Let's just click on it. Okay, so again, file systems, reiterate this point, everything's just bytes. A particular file type is just a particular encoding for bytes, so it knows how different programs, when they look at that thing, they'll know how to interpret it. The typical one you guys are going to see is like a text file. All your little .jl files you're going to make through this course are just text files, so you can edit them with a text editor. They'll be ASCII encoded or Unicode with Unicode support for Julia. So just had a little demo of that. And yeah, nothing too special there. We're just going to talk really quickly about CSV files. Like, you're going to see these all the time. I don't know, is anyone interested in going towards data science as a career? Is that anyone at all appealed by that? Yeah, you're going to get lots of CSV files. Trust me, it's going to be in your future. It's like kind of ended up as a de facto for people who don't know how to code. They'll give you CSV, and people who do know how to code will probably give you JSON. So they're kind of the two. So we'll introduce them now. You'll have seen them. You'll probably get protobufs from someone who really knows what they're doing, but that's unlikely. CSV and JSON, because they're dumb enough that most people know how they work. Cool. All right, so we've got a little thing. We talked about this before. Let's get a Julia thing and just repeat it so you can see it. Shift ++, start Julia. Using data frame. So tabular data, this, you all have seen an Excel sheet. Tabular data is universal. Like, this thing of like each row is going to be a new entry and the type of the variable is going to be up the top. You're going to get these things all the time. You can make these things in Julia with this thing called a data frame. The equivalent Python package would be something like Pandas. I'll call it a data frame in Pandas. So here, if you want to add, this is the variable name, and then we're adding an array of entries. This is like one way. There's lots of ways. I'd encourage you to go and look at the data frames documentations because there's lots and lots of different ways to construct data frames. I know Andy's going to go over this stuff again because it's so useful. This is just, hey, I'll point at it. You can look at it, get an idea of the pattern. think that's fine. So we've got names, which are strings, ages will be ints, and gender. Have I shown you this? Is this a symbol? Has that come up before or not? I've lost. It's like a string, but it's just fixed. If you want to do that, there's two ways you can construct that. Like if you go A equals Paul, type of A, that's kind of symbol. You can construct it with this little colon before the thing, and you can make it that way. This one will probably be in your homework. Some of you are probably going like, I want to make a data frame column name hash. Has that come up for anyone yet? Yep. You can construct it this way, SYMBOL, and put a string in here, and it will turn the string into a symbol. This one gives you a bit more flexibility if you've got funny characters and you don't know how to make it. You can do it that way. Yeah, I won't say too much about what symbols are. That just, yeah, I won't say too much, but that's just the thing. So we've got a data frame that DF we made. So it's got 3 typed columns. So funny one here is we've given a missing value for the gender for Ella. So we've got string, int, symbol with a missing value. So this is really useful. Like when you get data, there's always going to be a value you didn't measure. And it's nice to have this differentiation between like, is it actually missing? Is it nothing? Or is it nan? Like all those different types, you know, you'll have to worry about that when you get real measurements. Like, did the sensor explode? Did it hit its saturation limit? You know, they kind of mean different things, or is the data just missing and you want to do something with it? It's a question for the people who are going to be on the statistics side is like, what do you do with missing data? It's really annoying because there's nearly always missing data. How you fill in those values when you try and do anything like machine learning, that's very interesting. Okay, so that's a data frame, and we can use this package called CSV to write this out. This is kind of annoys me that you always put the name of the file first and then the thing you're going to write out with this one. I always get it wrong when I go to do it myself. So where do I want to write it? Oh, I don't know my path. Anyway, people.csv, and that will write out this thing called CSV is a comma separated variable. So each of these rows will write to a thing called home Paul Billette. I talked about the shell last time. Julia has a shell too. If you press semicolon, you get a bash, little like bash thing you can do in Julia. So all the things I was showing the other day, you can do it in Julia too. You don't need to run bash. So that's Control C to get out. And I can't show you, I have to tell you, you press semicolon to get into the shell. Really useful sometimes if you're shelling out to run other programs. So anyway, that's the thing. Oh no, CD poll alert. I don't know where I am, PWD, and we're going to cat people.csv. Okay, that's, remember cat was just to write it out, to stand it out. You can do this thing. You can look at that thing. If I went into VS Code just to look at it, you'll see file, open file. There's people. Okay, so you see this is just an ASCII encoded thing. We've got those things that we put in as the column names, ages, gender, just get written up as the top as a header. In between is a comma. That's why it's CSV, comma separated variables. So you'll get into trouble if you try and put a comma in the string, because you get really confused, so don't do that. So this is called a delimiter. You can have like arbitrary delimiters, like there's also tab separated variables, but people don't tend to use those, they tend to use commas. But the delimiter splits, so splits the variables. So this top one will be the header with names, ages, gender. We put the names down there, ages down there, all separated by commas. It's pretty straightforward. Don't think there's much to say. If you want to, you can make it like you've got these optional arguments to CSV when you write. You can write and read whether the header is there or not. So we could get this symmetrically. We could go, let's see what happens if we get in df equals csv.read /home all that people. And this one, slightly confusing, is you have to give it a sync. when you take a CSV, I'm going to take the thing in people.csv and push it into a data frame. So let's call that df out, see what happens when we go the other way. Okay, so can't support this special type of symbol. If you notice, that's gone away for the gender, like that came in as a symbol. In the original DF, we had that as a symbol. Got this funny string 7 thing going on as well, but don't worry too much about that. But just a limitation of the data format. Like it's all it can do is like text, right? And it might have a guess that this variable type's a number based on what it looks like. It'll have a guess at trying to get the type back right, but sometimes it'll fall over. Yeah, that's basically it. I don't think there's much to say there. You also have this funny syntax where you can do csv.file and redirect it into a data frame. This is much like doing the redirect I showed you in the command line, same sort of thing. And you can read it with no header. So if you want to do that. Yep. Oh yeah, sorry. I'm about to move it over actually. Better? No, I got to look at this screen, not this screen, so I can see what you guys can see. So that way I said, oh, you get this optional header. I've said header equals false, and then it will stick the header in as a column and it'll get really confused. So you've also got options for skipping, all that stuff. I guess there's not much more to say. There's something about data frames. That's more about data frames in CSVs. So if I want to get access data, df, I can get it by, there's a couple of ways you can access these things. I can go df gender, I can go df dot gender, will work, and I can go df, I can do it like I'm accessing an array, colon, comma 3. All those things will do the same thing. That's just a little bit about data frames, but that will come back again. I don't think that's so interesting, but good to see it in case you need to use it. Any questions on that? That was super quick, but it's pretty easy, yeah? Yeah. Oh, the shell in Julia. It is complaining, is it? Oh, well, should use Linux. I can't help you there. Yeah. Okay, cool. Yeah, CSVs, they're super straightforward. That's all I got to say on that. That was quick. That's good. Okay. Now, JSON, okay. Talked about dictionaries. Basically, JSON you can think of as a way of serializing a dictionary to a text file. So serializing, I mean saving to a file, if I use the thing. It's like dictionaries, as I said, are super useful. You probably have experienced this. I guess probably everyone here has had experience already with the homework. Has anyone not hit that question, getting the IPython notebook and reading it in as a JSON file? Has everyone started that question yet? Has anyone not started that question yet? No shame. Oh. You'll be onto it. It's fine. Yeah, it's basically, basic idea is that if we wanted to write a dictionary into a file, that's what we do. There's JSON. We've got an example of getting one of these guys here. JSON's ubiquitous on the internet. Like if you're doing web stuff, internet's just made of JSON flying around everywhere. I tend to use it. It's like there's more sophisticated serialization formats. Like there's a thing I actually use probably more often these days. It's called BSON, which is binary JSON object. So you can get better for the data types, and a couple of reasons, technical reasons I won't say too much. JSON's kind of one in a way. It's like there were historically all these different, I talked about Excel being zipped up XML. XML was really big in like the 90s or 2000s. It was more structured. But for that reason, it kind of is worse. There's this thing in software like worse is better. Like sometimes the bad thing wins. It's kind of strange, but JSON's super flexible as dictionaries are super flexible. It's got problems in the same way a dictionary's got problems. When you get to this bit of like poking around into some arbitrary JSON and trying to work out the schema, like how this JSON is laid out is kind of yuck. Has anyone noticed that? Like, or is it easy? Are you all smarter than me and you found it really easy to go through? It's kind of yuck if you don't know this thing called the schema. It's like, how is this thing laid out? What levels do I have within this dictionary? If I'm going to have to navigate through, it's kind of tricky. For the same reason, JSON is a bit yuck like that. So like if you get some arbitrary bit of JSON, it can be hard to dig through and work out what it's about. So this thing of not having a schema is kind of an issue. Just going to go, as we said, like we got this JSON, we're using HTTP, which is the library. I hope this Safe Blues is still up. Okay. So what we've done is a web request to this website. We're going to do a get, HTTP get request to Safe Blues. And we're going to get some random JSON from that website. So JSON.parse. So if you take a text file that's JSON and you want to parse it into a dictionary, that's what you get. So inside this thing in here, this strand web body, that was basically this big string here, you know, all through here. When you parse that, it'll turn it into a dictionary. So they're kind of like, you know, the read-write thing is you like parse and then you write it out as JSON. And this thing will end up being a dictionary again. So useful functions for dealing with dictionaries. Oh, strand web data, sorry, can't read. So first thing I do when I'm going to poke around in a random dictionary is go look at the keys at the top level and then sort of go down from there. So okay, I've got 3 keys, one called strands. Wish that was called a different thing, so just do it. We can go have a look through this thing. Oh, that's a thing. If we look at this, type of a vector. So JSON, you get these basic data types. Like at the bottom, it can either be like a number, a Boolean, or a string, or it can be a dictionary again, or it can be an array. So an arrays are ordered. That's the big thing about arrays. You know, that data structure, like first is always going to be first. If I write an array in JSON and read it back out, first thing's going to be first. If it's a dictionary, the keys are arbitrary. Can't assume they're going to be ordered if you iterate through them. So for dictionaries, it's kind of annoying because you need to know the keys, but it's good for that reason too. But for arrays, if it is really an array, like you've got something where there's a defined order, you want to keep this thing in, stick it in that way. So we've got this thing called strands. Let's see what the first one of those is. Oh, it's a dictionary. So you go through, type of, it's a dict. We can do this forever and just find out the structure of things. This is the kind of thing. It's got all these things. So you can just have this thing that just nests down forever, arrays, dictionaries. Down in the leaf nodes, there's probably values somewhere. And that's the kind of this experience of dealing with an arbitrary bit of JSON you get. And you're going to have fun because the IPython, the Jupyter notebooks are just JSON. Even though they're called IPython notebook, it's just JSON. But an IPython notebook, or sorry, old man brain, a Jupyter notebook, when it's reading this, it knows how to interpret the JSON to display it correctly. So that part of the program that's running the front end will take this JSON and work out how to make this thing laid out. We'll have particular fields it's looking for, like cells, I think they're called. Go through that, blah, blah, blah. Yeah, that's the kind of thing. You can do all these, once you know it's an array, you can do length, blah, blah, blah. Again, well, there's lots of those. That's JSON. Your IPython notebook's just JSON. It's just a dictionary though. And it can't like in Julia, the dictionary, you can have arbitrary types. Like any type I can have in Julia, like I can make struct foo x float 64. I can make an array of foo. Sorry. So I'm going to make an array with a struct of my own type. So I just made a new type, you know, Julia doesn't know anything about this. This is mine. I just made it now. And I could make a dict that goes X goes to X. And Julia's happy to make this a dict of my type. Like any type you can deal with Julia, you can have a dictionary of that type. If I try to serialize this to JSON, it won't know about my type foo and won't be able to necessarily serialize that thing. So, you only get these basic types of like number, string, Boolean, and then arrays or dictionaries of those things in JSON. Happy with that? It's pretty easy. Yeah, and if you've got questions, specific questions about the homework, come up and see me afterwards if you're stuck. It's pretty straightforward. It is, I'll acknowledge that it is disgusting to get an arbitrary bit of JSON and just work out what's in there. Like, it's hard to navigate through. And that's kind of the problem. As I was saying, this lack of schema with JSON is the same thing. It's kind of problematic. A bit more structure helps you navigate things. Cool. Okay, so some basic familiarity with plots. It's pretty essential. What do I want to say? Oh, that's from Joni's textbook. You can have a look at some plots he made there. Lots of fun things. Again, as I said, if anyone's interested in a career in data science, there's like three ends of this, like ends of the spectrum with this thing. Is like people at my end who are doing more back-end code. Like, it's like you're doing like hardcore algorithm stuff. That's a part of my career now, but I've done the other bits too during my career. Then you got this kind of middle bit where you've got to worry about, this is like sorry, I kind of lied. There's like the hardcore machine learning bit where you're working on algorithms, making models, making predictions. And you got this middle bit of like halfway in between where you're a software engineer working with those people to make it run for people. And then you've got this other bit, which is more of the people-facing part of it, of like, cool, you made some results. What do they mean? You've got to explain that to someone. And like, they're all equally valid and you'll do different bits during your career. Yeah, it's kind of funny because I'm old enough to when data scientist wasn't a career. I've sort of conspicuously avoided that title, but it's kind of what I've done. So that bit of communication is super important. Like, it's like something you should practice. Getting good at explaining how to do things and making good visualizations for results is like super valuable. People can just do that if they're good enough at it. If you like that bit of customer interaction. Hopefully when we get some of the other people in to do the perspective seminars, you'll see a bit of that part of their career. Like, a lot of communication of results is a big deal. So getting good with plots and getting good at like summarizing everything, you do this big bit of analysis, but if you can't communicate it to someone, it doesn't mean anything. Like, so working out, and one of the best ways to do that is with visualizations. Yeah, so plots is the default. Probably Makey is probably the cooler one now, but I'm not as proficient with that. So we've just got some basic examples of plots, and you've done this yourself. What do I want to show? I don't know how much I want to show all this stuff because it's like, maybe there's just some examples of things you've seen, you'd like to see, like how to get labels on. That's pretty simple. You just do this label. The plotting documentation can be a little bit weak, I would say. It's kind of a flaw. It's like, can be hard to work out. Like, you go like, okay, I want to change the font size for the x-axis. How do I do that? You got to go look for the magic spell that tells me x font size equals blah, or change the font type and things like that. But you can do all that stuff. It's just, you kind of got to do a bit of digging. I think for this one, I find maybe the simple one is just like, so this in place stuff. So what do I want to do? So if I go x equals, these plots are way cooler than anything I'm going to do right now. So x equals x. Okay, so if we go plot xy, oh, I didn't use some plots. That would help. Just how you add things to the same plot and do multiple plots. So if I go P1, so we'll just do the basics to start with. So I go plot xy. Okay, I've got a quadratic. And then if I want to add something to it, go title equals And then hopefully title my plot goes in there. So you can do this same exclamation mark to edit the thing you're working with. Is that you do that in the plots library as well. It's more useful when you're going to do something like P1. So you give this thing a handle, and then if I want to plot, give it the handle. And of course, say I want to plot something else. I'm going to go P1 equals plot. So I'm going to have another plot handle with a handle P2. Oh, that looks messy. So I did something silly. Title my other plot. So whatever's come up there will be the second one, my other plot, where I've just done the negative of that quadratic. Then if I want to plot these two guys together, you go take those two handles, plot 1, 2. Then it will stick them on the same plot next to each other. That's really useful to know for all your little layout stuff. You can get really fancy with the layout. I can't remember, probably don't have this. And do that. So you give it a tuple and a layout option, and you go above or beside if you want to do all that stuff. Useful to know. Any questions on plotting? Is that easy enough? I think this probably might be something cool. I'll have a quick look through here. Yeah, just use this as like a reference for like when you go to do a plot for your assignment, if you can't work out how to put the legend, how to move it around, there might be some examples here. The internet's full of that stuff, how to do a histogram. That's all fine. This one's really cool. I can't remember, for question 15, did we say you have to make an animation or? Yeah, so this is like an example of that. So that one's a good one to do. A good one to look at this one. So we've got a function graph creator where it takes n as an int. It's going to make vertices from 1 to n. And it's using complex numbers to make a circle. Hopefully you can see that. Pi, blah, blah, blah. And so using the real and imaginary parts of this complex points, let's just do it to see. So we say n equals 2. So we get an idea of maybe n equals 3 is more interesting because we'll get 3. So vertices equals 1 to n, complex points. We'll just copy these guys across so you can see what's going on. So it's going to make 3 imaginary numbers around the unit circle. Then we get the chords by the real and imaginary parts of those. So there's one, should be like 1 pointing up, 1 pointing over there, 1 pointing over there. Just to get the plot coordinates and then turning these into coordinates. Yeah, that's fine. And then making edges by joining them together. So this bit though is the bit you'll need to know, the little magic spell. There's a macro for doing this too, if you don't want to do it this way. I think it's called @animate. I think that's. I'll come back to you on that one. I can't quite remember. Anyway, you can just use this one. But animation. So this one's, it should have a little exclamation mark here. This one annoys me that you plot something and then you use this frame method on animate to add the frame to the plot. And then that will give you, you can save this, make a GIF of this animation. You can also make MP3s and stuff, whatever, MP4s, but and with a frame per second option. So this one above with 16 makes this sort of cool looking plot where it iterates through and draws the edges of a complete graph of this thing. Yep.
If you want to remove points, you have to delete the entire
well, it depends how you've set up your data structure, right? Like you could delete from the array and just plot the array every time. Like you could use delete at is probably what I would do. If I've got an array of stuff and I'm going to plot it like an X series and a Y series, and I've got a particular one I'm going to want to get rid of, I'd delete at for that element in that array.
Right, but it seems like the code in this example, it just keeps flying without wiping the plot.
It keeps, say that one again for me.
It doesn't wipe the plot.
Oh yeah, no, that's because of this plot, right? Like you could redraw every time if you wanted to. That's just to make, you iterate through and draw the new edge on. So rather than drawing all the edges every time, but you can totally do that too if you want. That's pretty fun. I think like for people who maybe visual and like starting to do coding. Like I know lots of people who've fallen in love with coding because of visualizations. Really good friend of mine was doing a PhD in physics and they kind of hated it and they got really into doing computer rendering, and they worked on an open source project and ended up making friends with someone who won an Academy Award. So that's really strange. They work for Sony DreamWorks. It's really weird. So, you know, you completely fall for this stuff. Like if you're a visual person, I don't think I've made anything cool. I think I had something that is not, I think I can show you this as an example of, oh yeah, so this is Julia getting better. So when I first used Julia in like 0.3, I didn't have the animate little function to do this stuff with. It didn't exist back then. So I had to make a JPEG for every frame, save them to disk, and then run this program called FFmpeg from the command line to make a video from all the frames. Not going to work with that editor. But like this is just for like when you want going to learn something new, try and make something you want to make to see if it's fun, like to make it fun for yourself. Like this is one I made ages ago. I did solving the wave equation in 2D and adding point impacts and solving the PDE in each frame. So that was what that was. That was something I made years ago to try and learn Julia. So yeah, simple thing. Simple-ish, a lot like doing this ODE one that's going to come up for you guys. So pretty simple. Cool. Yeah, so I'd just say that's just saying that because like visualizations, I think they're kind of fun. You know, I like maths, so make a mathematics visualization. It's a good way to learn a programming language. See if you can work out how to do things. That was awful making that thing because I didn't get this animate function. It was really, really hard. Cool. I guess the other thing you're going to want to do, good packages to know are statistics and stat space. What do I want to say there? Not too much, but all these basic, you know, basic statistical things you're going to want to do. You have support for that. So it's kind of annoying because I always do this, like I'm on the stat side of the fence these days. It's like nearly all the time I'm going to do something like, okay, what's the mean of X? And I go, means not defined. God damn, it's not in base. So have to go using stat space. 5. That's cool. And you'll get all the basic median, mode, type. You know, you can do all these basic things, you know, all the basic statistical steps. Yeah. All these little basic summary statistics things you might want to do. Including like harmonic mean, geometric mean, blah, 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 arithmetic mean, gets called mean. Useful one to know, I'll just say, if usually like this is a nice little convenience thing, like usually you get this random array and you want to go like, what's the biggest value? What's the smallest value? Sometimes you want both. If you want the range, the function for that one is extrema. If I can type. X, cool. The other thing you might want to do is, you know, maximum. Yeah, sometimes you want the maximum, sometimes you want the argmax. So guess what the function's called in Julia to find the argmax? Argmax. You don't like, I mean, in other languages, you're going to go do something dumb like X equals blah, blah, blah. Find first. You don't have to do this sort of silly stuff. You can go argmax. Hey, it's already in there. That's nice to know. That'll help you out when you know, if you know that exists. And it's just like the mathematical version of argmax, where you want the argument that maximizes the function, not the maximum of the function itself. Cool. Yep, cool. Numerics, that's where I wanted to get to. So all that stuff is fast. You can work that out yourself. All the notes is there. Okay, this is important and subtle, and it's probably like this, as a person doing applied mathematics, floating point you know, you're always going to be working with the real numbers. Like, so how do we represent the real numbers on a computer? And floating point, IEEE 754, I can't remember. There's a standard for this. Let's see what it says on Wikipedia. Yeah, 754. I nearly got it right. That's the standard for how we represent floating point numbers. So what we're trying to do, so you think about like a physics problem, the dynamic range of physics is terrifying, you know, like you go from an atom, like angstroms, out to like light years. So the dynamic range of the real numbers you're going to care about, huge, vastly huge. So you want something with this gigantic dynamic range. That's pretty much the starting point for motivating why you want to deal with floating point. So floating point is weird. It's not what I would have come up with. It's kind of strange in a way, and it has these subtle edge cases that I'm going to try and point out. So what we're going to do, got a little function here, pretty print float. So it takes an argument, it takes an input x of type float64. We know this bit string function, so it's going to turn x into bits, and then there's a sign bit at the front. So unlike signed integers, where, you know, it's got this funny 2's complement representation, it does just have a sign bit that says whether it's positive or negative out the front. Then there's an exponent, bit called exponent, which goes from 2 to 12. By definition of this standard, you use this many bits to represent the bit out the front, or the exponent, bit up the top. And the significand or the mantisses, these bits out the front, or the last few from 13 to 64. So let's just run that. So, what was the example they gave here? 15, I don't know if this is a special example, 15.324. So if I just type that in, type of X is a float 64. So 64-bit float by default for these floating point numbers. You can see you get float 16 if you're brave. That's like not much precision. That's going to cause you problems. Float 32 and float 64. So you want the big ones most of the time. Sometimes, like, as I said, like, not that long ago, a lot of operating systems were 32-bit. So using 32-bit floats was the thing. There's an infamous story about, it may or may not be true, so I won't say too much about precision, but yeah, there was a special representation for floating point on the, it caused a problem in the Iraq War. You can go off and read about that with missiles. Has anyone heard that story before? Yeah, anyway, go and read that. Okay, so type of this, and we're going to do size of X. Yep, so that's all standard, 64-bit, 8 bytes, 8 times 8, 64. Story checks out. Okay, we do bit string, we can see what this guy looks like. Cool. So that first bit is the sign bit. Let's check if I was lying to you guys. We'll make it minus, bit string. Went to 1, cool, I wasn't lying. Okay, and then the next bit, you get this funny thing, and then a bunch of funny things, and there's kind of a pattern in there that's kind of cool. Pretty print float X. So sign bit of 0, the exponent is this guy, and the significand, it's a really long bit to represent the front. You get built-in functions, exponent, it's 3, and can't spell that word. See if you get. Okay, and if you don't buy it, so the exponent's in base 2. That's the thing to remember. We're all dealing with. I'll just make this a little bit more painful. Hey, we got our number back. So 2 to the exponent times the significand. I should have put a sign bit. Do I get a sign function? I do. You could have done that too. Yeah, so that's how it's constructed. So it's basically scientific notation. So we've got a bit out the front for the sign bit. We've got a bit for the exponent. We've got a part of that bit string for the exponent and the part of the bit string for the significand out the front. So it looks like. Okay, you could do the same thing for float 32 if you really want to hammer on. And again, this standard is there's it's going to be from this range 2 to 9 and from 10 to 32 for the significand. So that's like, if you need to know that, you can remember that if you want, if you're doing this stuff by hand, but you've got these built-in functions that will do it for you. Okay, so what we're trying to do is any number on the real line with a finite number of bits. That sounds crazy. Like, that's a big thing with a little thing. So how do we cover it as well as we can? We're going to use this thing that's the floating point numbers. So each floating point number is represented this way. So we've got a sign bit, 1 plus f2 to the e, and e is a signed integer called exponent, and 1 plus f is called the mantissa or significand. And so, yeah, value of f is represented like that, and where they're binary values. Lots of stuff. So what do I want to show with that? Yeah, this is like, I would go through this yourself, because again, like, just to do this deconstruction stuff, you can go through that yourself. The pedagogic bit, I can say that word, it's a very big word. Is this not opening for me? Is thinking about how these things are distributed. So if I look at, it's got this picture, but it's kind of weird. If I were back in the 40s and they said, Paul, come up with a way of representing the real numbers, I would have gone for logarithmically. I would have taken the log of the numbers directly. Like, so it's like just like a log scale with a sign bit. And they didn't do that. They did this funny floating point thing. And the thing, maybe this isn't the best picture to see it, but what's going on here is that they'll be evenly spaced between powers of 2. That's the property of the floating point. So for every power of 2, you're going to have a fixed number of samples between that. So you go up to the next power of 2, fixed, 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 which is kind of strange. I wouldn't have come up with it that way. It's really quite interesting. But that's how, if you go turn the crank with that stuff, that's what you're going to get. So you're going to, there's this thing called machine epsilon, which is like the smallest floating point number you can deal with. This is pretty important. So when you guys are starting to do some tests of like, do some calculation in floating point, I kind of, as a consequence of dealing with floating point, that these things aren't filling the real line, you're always going to have problems. Like, it's going to miss by a little bit and you're going to have a bit of fluff. And this ends up being so important that you get this thing called EPS for your type. The default is for floating point. And this is like smallest relative change that you can deal with floating point is this number. This thing's built in, press up, EPS float 32 will be a bit less. So this isn't, 10 to the minus 16, you can deal with that. Like most problems, that much relative error is not going to bite you, maybe, depending on what you're trying to do. When you get to 32, this one is actually pretty problematic already. So 10 to the minus 7. And by 16, you're trash. Like, relative error, it's going to get you really soon. So it's like 64-bit is the way to go. Sometimes 128 if you need to. And this is just, to calculate this, if you go through this maths up here, it's like how big, we had it back up here in this pretty print thing. It's like basically how many bits for your significand are you using? So just 2 to that is what will give you those numbers. That's all that EPS function is telling you. It's just 2 to the minus 32. So this comes out as this thing of like, you sort of, due to this funny spacing, relative error is always going to be between machine epsilon. So you can't expect any calculation you're going to do to be more accurate than that. So it kind of sets an upper bound on how much precision you're going to have with your answer. So it's this thing that can actually introduce indeterminism. So like, it's like nearly like randomness that can come in when you're doing a lot of these floating point operations one after the other. You're going to get this little bit of fluff that propagates every time. This little bit of epsilon fluff. So got a demonstration of this here. What we're going to do, we're going to make, so these are numbers that don't have an integer square root. So we're doing set diff of the numbers between 1 and 100 and non-squares. This thing's going to cut out, 4, 9, 16, they'll all get chopped out. So when we go to take the square root, we're going to expect to get a real valued number back, right? Make sense? Cool. So what we're going to do, we're going to do this guy in float 32. I won't get the tilde. You can do tilde if you want to do that. Okay, so and we're going to pretend if we do the same thing with float 64 that it's so much more accurate that it lets us know how much error we've got on the 32-bit. So what we can do is we're going to look at the relative error between these guys when we take this one. And we'll see, again, I'll just copy the plot in. You could just look at the plot on the thing, but I think it's give you a bit of extra syntax. Done a scatter plot. So that's just the data with some labels. And then we're going to put in the floating point, this F's value for float 32. So they're kind of distributed within there, right? So this is, if I did square root using float 32, I'll pretend that float 64 calculation is so much more accurate that it gives me the error, and I can see how the residuals are distributed when I do it in float 32. Make sense? Cool. This is a leading question because it's going to come up with later on in the course, does that look random or structured to you guys? Well, vote random, put your hand up. Structured, somewhere in the middle. Yeah, I'd say it looks structured, right? So this actually isn't this is a leading question of here's a really weird way of generating randomness on a computer deterministically. All we did was calculate square root and look at the relative error between float 32 and float 64, and we got something out that looks kind of random. So question for coming up in the course is can you use a deterministic process to generate randomness on a computer?
Could you explain what's going on in the plot?
In the plot? So these are just for each of these samples. Each one of these scatter points is for each of these non-square numbers, it's looking at the relative error between float 32 square root, float 64. So if we look at the first element of those arrays, well, this is a problem with using these funny characters. I got to go get X tilde out. Maybe I just go up. We look at the first element of X tilde, and I look at the first element of X, or XX. They're slightly different. And that's because of with floating point in 32 and floating point in 64, you're going to get a different approximation of these things. And so each one of those scatter points is just that relative error. How big is the difference of those two compared to the value? Yep.
Where does that error come from?
It's just that you're using 32 bits to represent something that's a real number. You can't get, there's only so much, you're just basically going to the nearest one. You're not going to be able to lock right onto the real one, right? Because there's this spacing, there's holes in between all these spacings in the floating points. So you can't represent every one. Yep. Makes sense? So that's that guy. There's also some special values for nan, inf, and negative inf. So you get those as well. In floating point, they've just put away 3 special floating point numbers that give you negative infinity, positive infinity, and nan. Now this one is fun. So I'm going to do this before you get to run away. You can't actually, so I think this one's the most fun. So if you look at a number like 0.1, can't actually represent that as a floating point number. It's if I do the big version of that, don't get 0.1. It's going to be just missing. So this gives you a somewhat surprising thing that floating point numbers, this should work, right? That's the property of numbers. an arithmetic on real numbers, like you should be able to put the brackets wherever you want and you get the same answer. And we don't with floating point. So if I add 0.1 plus 0.2 first and then add 0.3, or I add 0.2 and 0.3 and then add 0.1, I get a different answer. It's kind of fun. So they don't. Yep, you lose associativity, which is fun, but you kind of get you get approximate associativity, so it's not that exciting. So if I go approx, which is a useful thing, they're true. If you wanted to look at the difference between these two, again, it's going to be this thing around floating point epsilon. So you lose associativity, and this has consequences. Another one that's fun is if I do this. So I've got 1e to the 9. I'm going to add 1e to the minus 9. And then it equals 1e to the 9. So this little guy just gets eaten by the big guy. So if you try to add a really small number to a really big number, bye-bye little number. It's gone. So because of these things, you know, like this loss of precision, doing silly things like adding lots of little things together instead of multiplying will cause big errors. Like these things can compound over calculations. Isn't so much of a problem here. You know, this is fake, but this error can get big. If you do stupid things, it'll get really, really big. And I guess I'll just quickly show you, and we're probably keen to get out of here, but this is like a sketch of how to add floating point, right? Well, we've got two floating point numbers with different exponents. We've got a equals 1, 2, 3, 4 plus 10 to the minus 5. B equals 2, 3, 4, 5 times 10 to the minus 3. And we want to go a plus b equals c. And we've only got this much precision in, we've got these floating points in decimal. And we've only got 4 out the front. And we've only got 1 for the exponent. So the way you can think of adding, this is not how it's implemented, but it's kind of just like a sketch of how you might implement addition. You shift them to the same big exponent. So you take this first number a, you're going to do this bit shift thing of like pushing them across. And these guys at the back, 3 and 4, just disappear because we lose them. And then we add them together. And then see, you're done. That's how you would do, that's a procedure for doing addition and floating point. And this gives you an idea of why when you do that little one plus a big one, the little one just goes away. Make sense? I got my last one, then I'll let you guys go. This is, I said, this one bites me. Every bloody 6 months, I get this one. So I'm going to use linear algebra. I'm going to make this funny thing where I've got pretend it's some data. And then I'm going to do the eigenvalue of, I'm going to try and do something like the eigenvalue of the covariance matrix of this thing. So who's done enough of this stuff to tell me what should the eigenvalues all be for this thing? No, they'll all be positive because greater than or equal to 0 is the thing that I would be expecting. So if I actually do this though, because of floating point, some of these guys go negative, and then there's a few little positive ones. There's a lot of zeros. Well, like there should be a bunch of multiplicity of zeros and then one that's really big. What actually happens when you do floating point on these things for the calculation, the way eigenvalues are calculated, some of them actually go negative. And if you've got an algorithm where you're assuming, like say, PCA would be the example of why you would do this thing. So anyone know what PCA is? Principal component analysis? Kind of, do you want to do 5-second explanation?
It's where you take the eigenvalues of the covariance matrix,
Yeah.
the data set, and you can see the dimensions, the one which varies most.
Yeah, so you can imagine if you've got like an ellipse of data, like fluff like this, it's pointing that way, right? So this example would be like it's really skinny and it's pointing just like it's like a line. And then I've done this eigenvalue decomposition to go, and it's saying like the standard deviation is imaginary in some of those axes or something. It's kind of gone wrong. So getting this code, I've had this where I'm assuming all these things are going to be positive, and the next bit of code, kaboom, like every 6 months, this happens to me. Nearly this is a really artificial example, but if you're just going like, oh, I'm going to do PCA on some points, and then some points happen to be in a line, you're going to get this degeneracy. When you go to do the calculation, it's a floating point, some of them end up negative. So you have to check. It sucks. So you end up doing an eigenvalue decomposition, checking if any are less than 0. If they're less than 0, set them to 0 and then reconstruct it. It's awful. Cool. That's a really quick introduction to floating point. We'll get on with numerical derivatives. Oh, sorry, yeah. Yep. It's small. Everything, you have to treat it like a, it's not exact. It's always going to be, it's an approximate solution, right? It's going to be close, and it's really about, you set up your algorithms to control floating point propagation, these floating point propagation errors. It's like, if you're being really serious about doing something like linear algebra, taking account of all those little errors and doing it in a way that's not sensitive to them will be the way that wins. So it ends up being quite difficult. It's just like, you're right, it's hard to get real things to work. So these things, like when we talk about linear algebra next week, using the linear algebra libraries, because someone very, very smart with a very big head has thought about floating point for a very long time and how you would do these things, and they've got it right most of the time. It's very hard. Yeah, cool. All right. Any questions apart from that? We're good. Oh, yeah.
When you did big 0.1.
Yep.
Why was it not all zeros at the end?
Well, because it's like, if I write 0.1, I'm writing 0.1 in floating point, in float 64.
Why can't you just set all the like significant bits to be 0?
Well, for that example, because it's 2 to the power, 0.1 in decimal doesn't fit nicely in that scheme. It's like just off. Yeah. All right. Okay, thank you. I'll end it there. Oh yeah, no, it's okay. I'll just send this out. Sorry.